Okay, we're going to determine the area that lies inside the first curve, but outside the first curve. Now, what they mean, the curves as you read left to right. So my first curve is r equals 2 cosine theta, while the second curve is r is 1. Now, they're both circles. The first curve is a circle that is not centered at the origin. The second is a circle that is centered at the origin. So if you're inside the first curve, here's what they're talking about. You're inside the first curve here. So we're going to talk about the area there. But you are outside the second curve. So the second curve is the unit circle centered at the origin. You have to be outside that curve. Okay, so what I'm demonstrating here is the area they're referring to is right in here. And this is what they're talking about here. So what I'll do now is I'm going to erase all this other stuff here because it's distracting. But that's what they're talking about. Area inside the first curve, but outside the second curve. All right. So we're going to need these points of intersection here. Okay, so going to be two angles here. Theta is one angle, and theta is the other angle. So we find those points of intersection, set the curves equal to each other. So I can say that this is 2 cosine theta. Maybe we could put this in red since it's points of intersection here. 2 cosine theta equals 1. This is the first r, and this is the second r. So we set these r's equal to each other. 2 cosine theta equals 1. Solve for theta. And cosine theta is 1/2. So opposite definition of cosine. Adjacent over hypotenuse. And here's the square root of 3. So a special triangle, as you guys can see. So that means theta is 60 degrees or pi over 3. And there we go. There's theta pi over 3. So here's my first point of intersection here. Theta being pi over 3. Now, remember, all students take calculus here. This is where cosine's positive. So cosine's positive in quadrant 1 and quadrant 4. So I'm going to use this angle of minus pi over 3. So the area that they're talking about is going to be between these angles here. What I think I'll do is find and use symmetry here. This is what I'm going to call A1. and double that area. Right, we're going to use some symmetry here. So let's call this portion A1. So the area will be 2A1, where A1 is the integral from 0 to pi over 3, 1/2 r outside RO squared minus r inside squared d theta here. So let's move everything over. So here's what we're going to use. And that constant is 1/2 here. So it's actually, you can put this constant inside or outside. And that's what we're trying to find. We have to get this r outside. This is the outside curve in blue. The inside polar curve represented by r. Blue and green there. R outside, R inside. And we're going to use this formula. This is the R outside squared minus R inside squared. And you have that factor of 1/2. So that's what we're going to use. All right. So here we go. So that take out that 2. So this area here is going to be 0 pi over 3 r out squared minus r in squared d theta. So this will be 2 times that 1/2. So that 1/2 factors there. It's gonna be gone. So we got to say, okay, what's the outside portion here? So we're going to draw an arrow here. Outside curve, inside curve. Now the outside curve is the circle here that is not centered at the origin. So it's 2 cosine theta. The inside curve is r is 1. So we got 2 cosine theta and 1. So here, this is the 2 cosine theta, and this one's the 1. So we get the integral to be 0 to pi over 3, 2 cosine theta squared. So we're going to square that one. Minus 1 squared. So here's what we get. 4 cosine squared theta minus 1 d theta. Now, use your identity here. Reduce the power from cosine squared theta. Replace this with 1/2 1 plus cosine 2 theta. Okay. 0 pi over 3, 4 times 1/2, 1 plus cosine 2 theta minus 1 d theta. 4 times 1/2 is 2. So 0 pi over 3, 2 times 1 plus cosine 2 theta minus 1. So we're going to distribute there. 2 plus 2 cosine 2 theta minus 1. And you end up with 1 plus 2 cosine 2 theta. Okay. So when you integrate, you're going to use u substitution over here, where u is 2 theta. So remember, the derivative of sine is cosine. So when I integrate cosine, I just get sine. So here's what this becomes. Theta plus 2 times 1/2 sine 2 theta, evaluated from 0 to pi over 3. And 2 times 1/2 is just sine, so we'll say theta plus sine 2 theta, 0 to pi over 3. Pi over 3 plus sine 2 pi over 3 minus 0 plus sine 2 times 0. So this portion is just 0. Pi over 3 plus sine 2 pi over 3. So this is actually 120 degrees. All students take this is a quadrant 2 angle. Square root of 3 over 2. So our final answer, pi over 3 plus the square root of 3 over 2. And there we go. All right. Pretty good. So if we go to the next kind of curve here, we say we have area inside the first curve. The first curve is a cardioid. So the area inside the cardioid. And then area outside R is 1, and R is 1 is a circle. So it's outside that circle here. Okay. All right, so area inside the first curve, which is the cardioid, but outside the circle. So as you guys can see, they're really talking about this down here. This is what they're talking about right in here. All right, so I'm going to get rid of all the other stuff so it doesn't distract us. And we'll see how to do the rest. All right, so let me point out some points of intersection here. Here to here. And, you know, I mean, I could, unfortunately, just how this is designed, I have to reshade everything here. So if I were to do the algebra and set my curves equal to each other to find the point of intersection, R equals R, I'm going to get, you know, the following here. So if you said, what if you set the curves equal? R is R. Well, 1 minus sine theta is 1, or minus sine theta is 0. Sine theta is 0. That means theta is 0, pi, 2 pi, etc., right? So this is the angle here that we're trying to find. Let's try to do this here. These are the angles. So, I mean, this is the points of intersection that I try to find. Now, we're trying to get, you know, we're trying to rotate the angle theta to get this shaded area. Remember, we're going to have this inside area, you know, let's kind of look at it this way if I can. Put an arrow here. Okay, so here's my theta. Now, I know in red, if I can erase some of this, since I know where that came from, These are my angles here for this point of intersection. I don't even have to solve a trig equation. That's theta and 2 pi, by the way, right? If I rotate that pole, 0, 2 pi, 4 pi, whatever, okay? Now, this would be, if I rotate my pole clockwise, now I have over here, theta is pi, and then add a multiple. This will be 3 pi, 5 pi, and so on. So when I try to find the area here of this region, I can do it this way. I can say this angle theta in general is between, if I put it here, theta will be between pi and 2 pi. So I can start with my lower limit being pi, and I rotate all the way to the upper limit being 2 pi. So I have this increasing theta here. So the area now, remember, is 1/2 pi 2 pi r outside squared minus r inside squared d theta. So r outside minus r inside. Now, the outside curve here is the cardioid in green there. And in purple is the circle. So the cardioid is 1 minus sine theta. So if you can see that there, this is the green curve. Here's the cardioid. So that's what I'm going to replace that r with. And I guess this is purple now. The circle, r is 1 there. So 1 minus sine theta and 1. So I'm going to replace that right in here. 1 minus sine theta and 1. So we have 1/2 pi to 2 pi. 1 minus sine squared theta minus 1 squared. And this is d theta now. So we get 1/2, we integrate from pi to 2 pi. Now 1 minus sine theta times 1 minus sine theta here, minus 1. We're going to have to use FOIL. One minus 2 sine theta plus sine squared theta minus 1. So get rid of your 1s. I get 1/2 pi 2 pi. And I'm going to put the sine squared theta first. Now, sine squared theta here is 1/2 1 minus cosine 2 theta. So use your power reducing identity there. For sine squared theta, all right, let's see what we get now. 1/2 integral 1/2 1 minus cosine. Well, let me be careful here. Put a bracket. 1 minus cosine 2 theta minus 2 sine theta d theta. Okay. So inside 1/2 minus 1/2 cosine 2 theta minus 2 sine theta. Okay, so that's inside my integral from pi to pi. I have outside that 1/4 You know what I'm going to do? I'm going to multiply. I'm going to put that inside that 1/2. I'm going to take this factor, put that inside there, and I'll end up with, right, 1/4. I have to distribute that, though. Minus 1/4 cosine 2 theta. And then 1/2 times 2 is just sine theta. And there you go. So it looks like we're going to have to integrate this. Yeah. Okay, so let's integrate this. 1/4 theta. Now here we're going to have to use u sub, so let's be careful here. And u is 2 theta. So the derivative of sine is cosine, so that'll be 1/4 times 1/2 sine 2 theta by u substitution. And the derivative of cosine is minus sine, so this will be plus cosine. From pi to 2 pi. Okay, so plug this in. 1/4 2 pi minus 1/8, now double 2 pi, 4 pi, plus cosine 2 pi, minus 1/4 pi minus 1/8 sine 2 pi plus cosine of pi. So we get pi over 2 minus 1/8. Well, let's do a couple of things here before we do that. Let's get rid of some things. You know, sine of 4 pi, by the way, is 0. Cosine 2 pi is 1. Sine 2 pi is 0. Cosine pi is negative 1. So now I'm going to do the multiplication of 1/4 times 2 pi will be pi over 2 plus 1 minus 1/4 pi minus a minus 1 is plus 1. So we get 2, and let's say this is 2 times 2. So we get 2 pi over 4 minus 1/4 pi. So 2 pi minus 1 pi. So we're going to get 2 now. And it looks like that's going to be plus pi over 4. So there you are. And this is how we do this particular question here. So there we go. Okay. All right. So area inside. Here's another one. Area inside the first curve. So we say, what's that first curve? I think we do it gray, or let's get the highlighter. Can you see that? R squared is 8. R squared is 8 cosine 2 theta. Here's my curve. Area inside that curve. But then the second curve, I guess, is in blue now. This is 2. So outside that curve, outside the circle, radius 2. So if you can see these here. So here's what it kind of looks like. Area inside the first curve here. But outside the second curve. So we'll use blue. Let's go in another direction. So this is a circle radius of 2 outside that circle. Oops, there we go. So what you guys can see, here's your area now. And we got points of intersection. So we're trying to find the area there. So let's get rid of all this other stuff here so it's distracting here. So then the question is, where's these points of intersection? Let's try to draw an arrow. Anyway, okay. We got to locate the points of intersection here. So set the curves equal to each other, right? We want, but we're going to have to square the second curve. So this is r squared is 2 squared, which is 4. So if we use red, I guess, r squared is r squared. So the left, we got 8. Cosine 2 theta will be 4 now, because we squared this first curve over here. So we get r squared is 4. And that means cosine 2 theta is 4 over 8, which is 1/2. So we're going to have to consider, this is 2 theta, by the way, that angle. Definition, adjacent over hypotenuse. And again, here's what we find. 2 theta will be, looks like it's going to be 60 degrees again, pi over 3. So that'll mean theta is pi over 6. So this angle here is theta is pi over 6. Now say here's theta is minus pi over 6. And, okay, we're going to use that. So here's what I'm going to also do. Let me get rid of some of this so that it's not distracting us. We solve this trig equation. Okay. And let's write that nicer. Now we're going to use some symmetry here, ladies and gentlemen. I'm going to try to use some symmetry here. So take a look at this. This is going to be my axis here. This is theta equals 0 now. So I'm gonna call this A1 now again. So I'm gonna have to find this, because of symmetry. I got really 4 sections here, and they're all the same area. 1, 2, 3, 4. So I can say the area will be 4 times A1. And we're going to now have to find that inside-outside curve. So here's an arbitrary theta. So theta is going to be between 0 and pi over 6. So we know 0 less than or equal to theta less than or equal to pi over 6 here. And the outside curve, your infinity and your circle. So the area will be 4 times 1/2 from 0 to pi over 6, r squared out minus r squared in. And the r squared is this curve right here. 8 cosine 2 theta. So it's already squared. It's already r squared. So I'm just going to replace this here with 8 cosine 2 theta. And this is 2 squared. So it'll be 4. So r here is 2. This is the second curve. R is curve. So that's like the inside curve. So we got the outside curve and the inside curve. So all together, let's see what this area becomes. 2, 0, pi over 6. This is 8 cosine 2 theta minus 2 squared, which will be 4. So we're going to keep this 2, 0, pi over 6. 8 cosine 2 theta minus 4d theta. And, you know, I'm going to put that 2 inside. I mean, I can factor out the 4 and so on, but I think it'll be easier to just integrate if I have that constant. So 16 cosine 2 theta minus 8. All right, so I'm going to integrate here. Don't forget, this would be u sub, where u is 2 theta. So derivative of sine is cosine, so that'll be 16, 1/2 sine 2 theta minus 8 theta from 0 to pi over 6. And this will give me 8 sine 2 theta minus 8 theta, 0 to pi over 6. So 8 sine 2 pi over 6 minus 8 times pi over 6 minus 8 sine 2 times 0 minus 8 times 0. So I'm going to deal with the, you know, sine of 0 and 0 portion. That portion is gone. So I get 8 sine, and it looks like pi over 3 minus 8 pi over 6. Okay. So pi over 3 is 60 degrees. And sine of 60 degrees is going to be square root of 3 over 2. So you get 8 times that square root of 3 over 2 minus 8 pi over 6. So it looks like that's 4 square root of 3 minus, simplify 8 over 6. 2 goes into 8 4 times, and 2 go into 6 3 times. So 4 square root of 3 minus 4 pi over 3. So there we go, ladies and gentlemen. So that's getting the whole area all at once. You know, we're going to look at that property of symmetry here. 4 times that, and this is what you get. 4 square root of 3 minus 4 pi over 3. Anyway. Let's try this again. Area equals 2 plus sine theta. Well, let's see. First curve. Area inside the first curve. And the first curve is in blue. So area inside that first curve, which is in blue. So there's my first curve. 2 plus sine theta. That's the curve you're looking at in this blue. If you can see that, the blue outline. The green outline, the green curve here, is RS3 sine theta. So it has to be outside that curve. And that's a circle. It's not centered at the origin, but it's a circle. So we want outside this circle. So what you should see is this. This is what they're talking about. All this area here. It's kind of interesting. Kind of nice. Okay, well, let's take a look here. And, a little bit of that blue portion. But you guys seen what we had to do, so let's do it again. So we're going to use some symmetry here, ladies and gentlemen. And so, if we actually see the points of intersection here, there's only one point of intersection. It's right here. So if we set the curve, r equals 2 plus sine theta and 3 sine. So sine theta is 1. Let me show you what I'm talking about here. So we say if I set my curves equal to each other, right? You get 2 plus sine theta will equal, this is 3 sine theta. So we don't have space, but we'll do the work down here. R equals R. So we say 2 plus sine theta here will be 3 sine theta. So, okay, 2 plus sine theta is 3 sine theta. So this means 2 will be, if I subtract sine theta from both sides, and that means sine theta, is 1. Sine theta is 1 at pi over 2 from 0 to pi over 2. So if you said to me, is that why the point of intersection here, this only point of intersection you're trying to draw? Is that theta being pi over 2? And the answer is yes. Okay, I'm going to get rid of this second and first. So you guys can see this is that point of intersection at theta equals, pi over 2. So I might draw my theta being just something like this. Here's an angle theta. So I want to figure out how I want to integrate to get this outside-inside curve. Now, one strategy would be is if I just said to you, let's find a color. Let's find purple. Here's where theta is 0. And if I rotate counterclockwise 1 full revolution, outside curve is in blue, inside curve is in green. If I just rotate from 0 to 2 pi, here's one way I could do this. I still have the outside curve in blue, green for the inside curve. Just rotating, here's my theta, outside, inside, no matter what. Even this is blue. So I can do a couple of things. I can actually, just rotate from 0 to 2 pi. Because even if I did symmetry, I took half the curve. I can figure out from maybe a minus pi over 2 to pi over 2. But, 0 to 2 pi are some very good values to use to evaluate the limits. So here's what I'm going to do. I'm not going to use symmetry. I'm just going to use the idea that fundamentally that outside curve remains the same and the inside curve remains the same, irregardless of that angle theta. So here's kind of a straightforward kind of thing in the sense that the area will be 1/2 the integral, I'll say from 0 now to 2 pi, just one full revolution counterclockwise, and I'll get the square the outside curve minus squaring that inside curve, where the outside curve again is in blue, which is 2 plus sine theta. So I'm going to replace that with 2 plus sine theta. And the inside curve, the green, is 3 sine theta. So this will be 3 sine theta. So, all right, 0 to 2 pi, 2 plus sine theta, we will square this, plus 3 sine theta, and that'll be d theta. So yeah, we'll do, if you want to do the blue-green colorization here, this is what I mean. This is my blue curve, and this is that green curve, 3 sine theta. So there's, we'll have to square. Use FOIL here. And just square over here. One half. 0 to 2 pi. Now, 2 plus sine theta squared is 4 plus 4 sine theta plus sine squared theta. And that's just using FOIL for the blue curve. Right? 2 plus sine theta. First term is 4. Yeah, 4 sine theta plus sine squared theta. And then this will be plus 9 sine squared theta. All right. D theta. 1/2. 0 to 2 pi. 4 plus 4 sine theta. Sine squared theta plus 9 sine plus, that's 10 sine squared theta. And that'll be d theta. So now sine squared theta here can be used. And that's a half angle. 1/2, 1 minus cosine 2 theta. And that's kind of nice. 1/2, 0 to 2 pi, 4 plus 4 sine theta. 10 times 1/2, that's 5. You get 1 minus cosine 2 theta. It's d theta. 1/2, 0 to 2 pi, 4 plus 4 sine theta, plus 5 minus 5 cosine 2 theta. D theta. 1/2, 0 to 2 pi, 4 plus 5, that's 9, plus 4 sine theta, minus 5 cosine 2 theta. And what I might do is just put that constant back in 1/2, like I've been doing. So I get 9/2 plus 2 sine theta minus 5/2 cosine 2 theta, d theta. So you end up with, when we integrate, 9/2 theta. Derivative of cosine is minus sine, so this would be minus 2 cosine theta. Over here, you're going to use the u sub, where u is 2 theta. Minus 5/2 times 1/2 sine 2 theta from 0 to 2 pi. 9/2 theta minus 2 cosine theta minus 5/4 sine 2 theta, 0 to 2 pi. 9/2 times 2 pi minus 2 cosine 2 pi minus 5/4 sine 2 times 2 pi will give you 4 pi minus 9/2 times 0 minus 2 times cosine of 0 minus 5/4 sine 2 times 0 will be 0 here. So we might just say this portion is 0, cosine of 0 is 1, sine of 0 is 0, sine of 4 pi is 0, cosine of 2 pi is 1. So we could kind of scroll through this and get some nice answers. So we get 9 pi minus 2 minus a minus 2 is plus 2. And double check, ladies and gentlemen, it just simply seems like the answer is that 9 pi. Let's double check our work. Well, anyway, looks like the answer is 9 pi. Hopefully that's what it is. All right, let's look at this last one. Yeah, we're almost done. We got the last one here. Okay, got a circle for the first curve, so area inside the circle for the first curve. Purple curve, area inside, and purple. And then outside the cardioid. So what you can see now looks like this. Area inside the first curve, but outside the second curve. So let's try to erase everything now. And again, we'll have to do that portion again. Okay. This location, this location. So set the curves equal to each other. R equals R. We'll find the points of intersection. So 3 cosine theta then is going to equal 1 plus cosine theta. So subtract cosine theta from both sides. 2 cosine theta is 1. Divide both sides by 2. And cosine theta is 1/2 here. So theta adjacent over hypotenuse square root of 3 looks like 60 degrees again. Pi over 3. Okay. So that means theta is pi over 3 here. And I can say theta is minus pi over 3. So what I think I'll try, yet again, is theta will be 0 here. A1. So my area will be twice A1. Double that area. And that'll be from 0 to pi over 3 now. So I can erase all this work for finding the points of intersection. So then my area now becomes okay, 1/2 0 to pi over 3 r outside squared minus r inside squared d theta. Here's an arbitrary theta now from 0 to pi over 3. So the outside is in purple, which is your circle, and the inside is in black, which is the cardioid. So the purple is a circle. Black is the cardioid. So the outside is in purple. So I'm going to replace this here. This is r. 3 cosine theta. Let's double check. Yeah, 3 cosine theta. And the black curve is a cardioid, 1 plus cosine theta. So I want to make sure purple and the black curve. Okay, we have to square those. But 2 times 1/2 is 1. So this is 0 to pi over 3. 3 cosine theta squared minus 1 plus cosine squared d theta. Zero to pi over 3. 9 cosine squared theta minus, that's 1 plus cosine theta times 1 plus cosine of theta, d theta there. 0 pi over 3, 9 cosine squared theta minus, let's do the FOIL there, 1 plus 2 cosine theta plus cosine squared theta, d theta. 0 pi over 3, 9 cosine squared theta minus 1 minus 2 cosine theta minus a cosine squared theta, d theta. 8 cosine squared theta minus 1 minus 2 cosine theta, d theta. All right, let's see what we can do. Power reducing. Cosine squared theta. Power reducing. One half, 1, looks like plus cosine 2 theta. Okay. So we got to be careful again. 0 pi over not 8. 0 pi over 3. Let me get that 8 there. That constant 8 times that 1/2, ladies and gentlemen, right here. This 8 times 1/2, it's going to be 4, okay? 4, 1 plus cosine double theta minus 1 minus 2 cosine of theta. And then there'll be a d theta there. So distribute the 4. 4 plus 4 cosine double theta, minus 1 minus 2 cosine of theta. 3 now. Let's see what's there. All right, 3 plus 4 cosine 2 theta. 4 minus 1 is 3. 4 cosine, then minus 2 cosine theta. And here we're going to have some u sub where u is 2 theta. So we're going to try that out. 3 theta. We're not going to integrate yet. We're going to integrate. I apologize. Let's integrate now. Let's try this out. 3 theta plus 4. Now this is times 1/2. Derivative sign is cosine, so that's 1/2 sine 2 theta. Okay. You have to integrate cosine. So it looks like it's minus 2 sine theta. Three times pi over 3 plus 2 sine of 2 pi over 3 minus 2 sine pi over 3 minus 3 times 0 plus 2 sine 2 times 0 minus 2 sine of 0. 0, 0, 0. 3 times pi over 3 is pi plus 2 sine 2 pi over 3 minus 2 sine of pi over 3. Okay, now remember, got to remember a couple of things here. Pi over 3 is 180 divided by 3, that's 60. So this is 120 degrees. This is 60 degrees. So this will be the square root of 3 over 2. All students take calculus. Looks like this is going to be the square root of 3 over 2. All right, so let's double check. So let's see what we get. Pi plus 2 times the square root of 3 over 2 minus 2 times the square root of 3 over 2. And then this portion is just going to be 0, so this answer is just pi. Anyway, okay. Looks like we have some space left over. All right, ladies and gentlemen. So this is how we find area inside the first curve, but outside the second curve. And so I approach this directly here. This area is just going to be pi. So that's interesting. This whole thing, in terms of area, we found to be just pi. This whole thing is pi. All right, pretty good. Okay, there we go.